Hello everyone, my name is Sultan Al and this is my final presentation about climate and comfort. I will begin the presentation with the outlines. Here are the outlines. At the beginning, the introduction, later the literature review and the aim of the project, and after that the location and the design proposal and the design builder system plan, and at the end the BREEAM as a sustainability rating system. At the introduction, the world of architecture is undergoing a radical transformation, moving beyond static structures to embrace dynamic and responsive designs. In this report, a simple kinetic facade will be studied for a medium-sized office building in London. Here is some example of a building that uses sustainable Al-Bahar Towers in Abu Dhabi. The towers have a unique facade composed of 2,400 movable aluminum panels that depend on the position of the sun in the sky to provide shade and reduce energy consumption. This is a clear illustration of the interest that the UAE has in using innovative designs. The Kolding Campus in South Denmark University is a sustainable building designed to optimize energy efficiency. Its distinctive feature is the use of kinetic facades, which are aluminum shutters that can open and close to regulate sunlight and heat. This innovative design, combined with other energy efficient strategies, has significantly reduced energy consumption and earned the building the Best Sustainable Building Award in 2015. Aim of the project that is the following will be achieved through this project: analyzing the base case, establishing a framework for optimal design, identifying and prioritizing sustainability strategies, incorporating kinetic facade, complying with BREEAM standards, using simulation tools like Design Builder. My location for this project is going to be in King Cross Road, located in London, the capital of England. Here are the weather data diagrams in London. The temperature range, it can be -5 to in winter, and it can be up to 30 in summer. And the relative humidity, it can be 58% in June and minus 80% in December. Now I will explore the proposed design in the coming slides. Here is the base case, the first case. The proposed design is a simple office building with glass and solid walls, but without any additional features like balconies or solar panels. In this case, the base case will be enhanced by making it energy efficient. Following changes will be made to the base case designs. The materials will be changed to the ones with the lower UV values. Balconies will be added to the building design. A green roof will be added to provide insulation and lower that energy demand of the building. Solar PV will be added to provide a renewable energy sources. Building upon the base case design to improve design, green roofs, solar panels, and materials will be changed. A kinetic facade system will be added that can significantly improve the building energy efficiency. The kinetic facade will consist of movable louvers that can be adjusted to control solar heat gain and daylighting, optimizing the building energy performance through the year. The design of this building is a simple and compact. Stainless steel perforated kinetic facades that move in multiple angles are used. In summer, these are used to avoid sunlight entering the building, and in winter, they are set to an angle that allows maximum sunlight to enter the building. The kinetic facade is perforated because it is energy efficient, and as an aesthetic pleasure, it's customizable to environmental needs, while it's acoustically insulates and protects against the weather. The proposed enhanced case design with kinetic facade, the optimized case. Here is the design builder study plan. In this project, all three cases, base case and efficient case and optimized case, will be studied in 2 seasons: summer 17 of July, winter 17 of December. The daily behavior will be studied during 3 office hours in each season: 10 a.m., 2 p.m., and 4 p.m. Design builder study plan for building with kinetic facade. The optimized case. The primary objective is to see the behavior and determine what angles of stainless steel perforated kinetic facades are suitable for the 2 seasons of the year, summer and winter. For each season, the study will be done at 3 different hours: 10 a.m., 2 p.m., and 4 p.m., and for 2 different angles: 0 degree and 45 degree. Choose an orientation for the building on site. 3 building orientations are studied to investigate energy consumption and select the most efficient case. with the least energy consumption. At the orientation angle of 35 degree, the energy consumption was 56.3, and on the orientation angle 125, the energy consumption was 57.5, and the orientation angle as 215, the energy consumption was 57.3 kilowatt. And based on the results, the orientation of 35 degree was selected. Here the used materials for UV values. In the base case, the concrete wall was composition of it was 203.2 plus 16 plus 12.7, and the U value was 1.278. And for the roof, it was 100 plus 12.7 plus 13, and the U value is 1.54. And for the glass composition, it was 3 millimeter glass, and the U value was 5.894. And for the efficient case and kinetic facade, for the concrete wall, it was 203.2 plus 284 plus 12.7, and the U value was 0.12. And for the green roof, 60 plus 100 plus 12.7 plus 13, and the U value it was 0.294. And glass, for the glass, it was simple glass, and the U value was 1.2. The U values of the selected materials are available from the Design Builder Material Library. The selection of materials is based on the location standards. The first case study, base case. The analysis results showed that the energy consumed by the base case can design building is 56.3 kilowatt. Solar gains of the first case scenario. The annual solar gain analysis of the base case scenario showed that the maximum solar gain is on 17 June, and the minimum solar gain is on 17 December. The values are 59.18 in 17 June in summer, and 13.09 kilowatt in 17 December on winter. The second case study, efficient case. The simulation results show that the energy consumed by the efficient case design building, lower UV value materials, balconies, green roof, solar PV, is 29.87 kilowatt. There is a significant reduction in energy consumption by the value. The solar gains of the first case scenario. The annual solar gain analysis of the efficient case scenario showed the maximum solar gain on 17 June and the minimum solar gain on 17 December. The values are 8.42 kilowatt and 1.86 kilowatt. Respectively, the solar gains are significantly lower than the base case scenario, indicating the design as energy efficient. The third case study, optimized case. Fully closed kinetic facade at 0 degree. The analysis showed that the energy consumed by the optimized case design building fully closed lamel is 17.04 kilowatt. The solar gain of the office space in 17 June summer was maximum at 6.09 kilowatt, and in 17 December winter, the max was 1.33 kilowatt. And for the partly open kinetic facade as at 45 degree, the result shows that the energy consumed by the optimized case design building open at 45 degree is 17 kilowatt, and the solar gain of the office space in 17 June in summer was 5.87, and 17 December winter is 1.29. The analysis shows the building with kinetic facades, particularly when the lamel are open at 45 degree angle, is the most energy efficient design, while both optimized designs, fully closed and 45 degree, perform similarly. The perforated kinetic facade offers the most sustainable and energy efficient solution. External wind and pressure analysis. The wind flow around the building plays a critical role in determining its energy consumption. High wind speeds can lead to increased heat loss or drain, affecting the building energy demand. Therefore, analyzing wind pressure and velocity is essential to designing energy efficient building. Here is the velocity distribution and the pressure distribution for the first case scenario, the base case. And the velocity distribution and the pressure distribution for the second case, the efficient case, as we can see here. Here is the velocity distribution and the pressure distribution for the third case scenario, the optimized case and the lamel fully closed. The third case scenario, the optimized case, and the limit open at 45 degrees. By analyzing the wind velocity and wind pressure patterns, the wind velocity and pressure are lower in the optimized case, building kinetic facade. This results in lower energy consumption, making the building energy efficient. Here is the daylight and glare factor for the base case in summer. For the daylight, 17 June, for the minimum and maximum lux, for 3 of the times, 10 a.m. and 2 p.m. and 4 p.m., the minimum lux was 0, and for the maximum lux was 2188 for 10 a.m. and 2509 was for 2 p.m. and 2215 was for 4 p.m. And for the glare of 17 June, for minimum and maximum candela was at for 10 a.m. it was 1119 for minimum, and 2 p.m. was 1117 for minimum, and 987 for minimum for 4 p.m. And for the maximum candela was 2002 for 10 a.m. and 2314 for 2 p.m. and 1668 maximum candela was for 4 p.m. Here is the daylight and glare factor for the base case for winter. In the daylight in 17 December, for 3 of the times minimum lux was 0, and maximum lux was for 10 a.m. to 2030, and 2415 for 2 p.m. and 2175 for 4 p.m. And for the glare for 17 December in winter, for 10 a.m. was minimum 1008 candela and maximum 1843, and for 2 p.m. the minimum was 1231 minimum candela, and for the maximum was 2148, and for 4 p.m. the minimum candela was 952 and the maximum was 1693. The daylight and glare factor for the efficient case summer. At the daylight at 17 June, at 10 a.m. and 2 p.m. and 4 p.m. the minimum lux was 3 for 3 of them was 0, and the maximum lux was 860 and 898 and 768 for 10 a.m., 2 p.m. and 4 p.m. And the glare was for the minimum and maximum candela for 10 a.m. The minimum was 906 and the maximum was 1790, and for 2 p.m. the minimum was 912 and the maximum was 1949, and for 4 p.m. the minimum was 768 and the maximum was 1573. The daylight and glare factor for efficient case in winter. For the daylight 17 December, for the 3 of the times it was 0 lux, and the maximum lux for 10 a.m. 601, and for 2 p.m. it's 850 and 726 for 4 p.m. And the glare for 17 December was minimum and maximum candela. For 10 a.m. the minimum was 899 and the maximum was 1586, and for 2 p.m. the minimum was 886 and the maximum was 1876, and for 4 p.m. the minimum was 746 and the maximum was 1483 candela. Here is the daylight and glare factor for the optimized case. In summer and in winter, the daylight was for the minimum lux for all of the 3 times was 0, and the maximum was for lux for in summer 778 for 10 a.m., 369 for 2 p.m., 320 for 4 p.m. and the maximum lux in winter was 570 for 10 a.m. and 312 for 2 p.m. and 243 for 4 p.m. And the glare for the optimized case in summer was minimum and maximum candela. For 10 a.m. the minimum was 1100 and the maximum was 2214, and for the 2 p.m. the minimum was 897 and the maximum was 1590, and for 4 p.m. the minimum was 710 and the maximum was 1506. And the glare in December in the winter season, for 10 a.m. the minimum and maximum candela was minimum 1001, and the maximum was 2147. And in 2 p.m. the minimum was 897, and the maximum was 1540. And in 4 p.m. the minimum was 701, and the maximum was 1436. And here is the daylight and glare factor for the optimized case as at 45 degree. In the summer and winter, the minimum lux was same. All of them was 0 lux at all of the times, and in maximum lux for in summer at 10 a.m. was 668, and at 2 p.m. was 289, and at 4 p.m. was 243. And the maximum lux in winter for 10 a.m. was 569, and for 2 p.m. was 243, and for 4 p.m. it was 184. And the glare for winter and summer, the minimum and maximum candle at 45 degree. In summer, the minimum was at 10 a.m. 1109, and maximum was 2274. And the minimum in 2 p.m. was 947, and the maximum was 1440. And the minimum at 4 p.m. was 701, and the maximum was 1436. And the glare for 17 December in winter, the minimum candle was 10 a.m. for 1009, and the maximum was 2032. And the minimum in 2 p.m. was 701, and the maximum was 1436. And the minimum in 4 p.m. candela was 610, and the maximum was 1206. The result of the analysis showed that the daylight and glare for the kinetic facade case with 45 degree proves to be the best. This scenario balances adequate daylight penetration and reduced glare. This angle of the limel optimizes daylight availability while at the same time minimizing the amount of glare level across various times of the day and seasons. The base case and the efficient case have relatively higher daylight and glare values, which results in a decrease in comfort due to overexposure. Additionally, the kinetic facade with the 45 degree opening has a lower daylight factors as compared to the fully closed kinetic facade. 0 degree allowing a relatively lower level of natural light and glare, hence creating a more comfortable and visually appealing indoor environment. The study aims to investigate the optimum angle of limel in a kinetic facade using Design Builder software. The results from the study can be utilized as the basis for developing an automatic system to control the movement of the facade at suitable angles according to weather needs. Adding renewable energy resources like solar PV can also reduce building energy consumption. The results obtained from the study will be compared with BREEAM standards to evaluate the performance of the design building. And here's the end of my presentation, and thank you very much, and feel free to ask any question.